of discipline. She's a chemical engineer at Wayne State University. She does work in control systems for detection of cyber attacks for physical systems. So what happens if you've got a physical system in a plant making chemicals or something like that, and something gets compromised, a sensor, or it gets hacked, that kind of thing. Let me say a little bit about her background. So she got her bachelor's degree in engineering, chemical engineering at UCLA, um, and joined the materials and process engineering department at Aerojet Rocketdyne for 2.5 years, then returned for her master's at UCLA in got that in 2014, her PhD in 2017, and since then she's been at Wayne State. She has received an Air Force Office of Scientific Research Young Investigator Award, National Science Foundation funding, including the prestigious Career Award. She has works both sides. She's gotten a Research Excellence Award at her institution, as well as an Excellence in Teaching Award. So that's quite commendable. And we're looking forward to your seminar, Helen. For the students that are online, we will have a survey at the end that will be given out as a link. So please make sure you fill that out. And then we'll let you go, maybe like you to go maybe 40 minutes and then have Q&A, something like that, Helen. So we'll let you go ahead, share your screen.
Great, thank you so much, and thank you so much for having me here today. I'm really very honored. So let me try to minimize the. Okay, I guess everyone can see, but let me know if you can't. So I'm going to be presenting today on our work related to cyber-physical systems. I'm going to be presenting some of our work related to cybersecurity of control systems. And then I'm also going to be presenting a little bit of our more recent work related to quantum computation for control. That's more on the cyber-physical systems side. We have looked at a little bit of some of the ways that it could be related to cybersecurity, but I'll just be giving some of the basics of quantum computation with control. And so I'm a chemical engineer, as was stated. And so when I talk about control, I want to give a little bit of background on what that means we're looking at, and specifically in a chemical engineering context. So when we have a chemical process, so this could be something like a refinery or a chemical manufacturing plant, we take some raw materials and we want to convert them into products at this plant. And when we do this, we have a lot of operating objectives, like to do that safely, to meet environmental regulations, to meet our product specifications, and make a profit. And so instead of continuously having people stand at, for example, every single valve and manipulate these, instead we use automated systems that continuously monitor and then externally intervene when they see that any of our objectives is not being met. And this is what forms our process control system. And so the basic way that a process control system works in industry is through this feedback loop. The idea is that we have our process, and then there's a variable called the output that we measure with a sensor. And then the sensor measurement gets compared against the value that we want that measured variable to take. And we call this value that we want it to take the set point. And so then there's an error between our set point and what we measured. And so based on this error, the controller, which is really like a computer, will run some mathematical algorithm to figure out what it thinks the actuator should do to reduce the error. And it will tell the actuator, do this, and then the actuator will do that, and then that will impact something physical at the process. For example, if the actuator is a valve, then a valve will open at the real system, and that will actually affect what's going on in a real physical system. And so the big question in my field of control design is, what is the algorithm that this control algorithm here is running? And so one thing that you can use, this is very common in undergraduate chemical engineering, that will talk about using a single input, single output type control design known as proportional integral derivative, or PID control. And this is a case where the control action or input is calculated according to this mathematical expression. And it says that the input to apply to the process should be equal to some function of the error between the set point and the measured value of the output, the integral of the error, and the derivative of the error. And so this has been a successful design in industry, but it doesn't handle everything. So there can still be challenges with this control law. And so that has been the reason that people have suggested maybe we can move to more advanced control designs. And often these are model-based, meaning that they'll use a dynamic process model explicitly for their design. So this mathematical model can be developed either from first principles modeling, so that will be things in chemical engineering like mass and energy balances and all the physics, or you can get your models from identifying them if you have input and output process data. And so then you have a model that describes your process dynamics, meaning how your process state variables change in time due to disturbances, inputs, and interactions between variables. And then you'll make a controller where it is specialized to this specific process model in order to help it outperform some of the more classical control designs in certain circumstances. And so usually in chemical engineering, we deal with nonlinear models. And so we'll have nonlinear model-based control. So the question might be, why is that? Well, here's, for example, one of the first kinds of chemical processes you would learn in a reaction engineering class. It's called a continuous stirred tank reactor. And in this case, we have here just some tank. We assume it's well mixed. There is some feed into this containing a reactant A, and it has an initial feed concentration and temperature. We have a heater in this reactor. Then we have a concentration of the reactant in the outlet stream and a temperature of the outlet stream. So in chemical engineering, we learn how to model systems like this from the physics, and we do what's called mass and energy balances. Those are basically reflections of mass is conserved, energy is conserved. And by doing those, we can end up with equations that look like this. And so these have nonlinear terms, like these exponentials being multiplied by concentrations. And the reason that we get these nonlinearities here is this is actually the reaction rate law, this part with the exponential and the concentration. So in chemical engineering, because chemical engineering is about chemicals and we'll have reaction rates, then therefore we usually have nonlinear models. And so we'll want to develop a general notation for talking about cases where we're controlling some nonlinear system. It doesn't only have to be this continuous stirred tank reactor, could be any chemical process or other process described with a nonlinear model. So to do that, I'm going to introduce this notation where X means the vector of the process states. So in this specific example, that would be things like temperature and concentration in the reactor. X dot is dx dt, or the time derivative of the states. U is a vector of the process inputs. So for example, here we might be manipulating the heat being applied to this reactor, and then that's our input. And W is a vector of disturbances. So for this example, that might be, say, that our feed concentration of the reactant is changing, but we're not able to directly manipulate that. It's just happening and we have to deal with it. Then that would be a disturbance. And so with all of that, we can now have this notation that means a system of nonlinear ordinary differential equations. So it says the time derivative of our state is equal to a nonlinear vector function of our states, inputs, and our disturbances. And there are many different control designs that have been looked at for trying to drive processes like this from some initial condition to a steady state of this system where the variables no longer change in time. And so I'm going to make some assumptions about this dynamic model that we're going to use going forward. One of these is that our states, inputs, and disturbances are all bounded. I'm also going to assume that this process is what I'll term stabilizable here, in the sense that we have an explicit nonlinear feedback control law, meaning that we have a control law that's an explicit function of the state. And this is able to make our origin or steady state asymptotically stable in the sense that there exists this function called a Lyapunov function, which has the special property that its time derivative is negative along the state trajectories of the system when it's under this controller h of x and when we're not considering disturbances. And it does this for all x in a neighborhood of our equilibrium point or steady state. And so this idea of asymptotic stability is characterized in this figure here on the right. So what we see here is this trajectory having an initial state and the state moving with time toward the origin. So that's a notion of asymptotic stability. And so here, this red region is something that I'm going to call a stability region moving forward. So this is the set of states where the value of the Lyapunov function is less than or equal to an upper bound. And then we also have this condition about v dot being negative. And so this controller h of x is able to give us a degree of robustness to disturbances and uncertainty, which means that even when we have disturbances or uncertainty, we're still able to drive our state toward the steady state. But even though it has those properties, it doesn't account explicitly for performance or constraints. And so that was the reason that people developed what's called Model Predictive Control, or MPC. So this is an advanced control law that's actually an optimization problem. So what that means is that it figures out how to operate the process optimally all the time. And so the way that it does this is it solves this optimization problem repeatedly. So what this says is it says that we want to minimize this time integral of a quadratic tracking stage cost is what is usually used. And what that means is that when the stage cost is equal to 0, which is the minimum, then we are at our steady state. So what this type of controller does if you use this type of objective function is it tries to drive your state to the steady state. And then we'll also have the dynamic model as one of our components of this control law, initialized from a state measurement, and then we'll have input constraints and state constraints. So we solve this optimization problem every delta time units, where delta is what we call a sampling period. This means we solve it at every sampling time tk. And then the solution is a piecewise constant input trajectory with n pieces, where n is what we call a prediction horizon, and each piece is held constant for a period delta, which is the sampling period. So this is more clear in this figure up here. So the idea is we want to drive our state toward the steady state. So let's say that this black line here is the steady state. Our goal is to try to drive the state toward that steady state. We have to predict what's an input trajectory that could do that over time into the future. So we'll make predictions. We'll say, okay, I think if the input takes this value for some amount of time, then this value for another period of time, then this value for another period of time, that eventually I will move toward the steady state. And so that's what a model predictive controller is doing, is it's predicting the input trajectory that will drive me toward the steady state with time, for example. It can do other things if we change the objective function. So we actually constantly solve this optimization problem because our model that we use in the controller never matches the reality. So we have to get feedback in order to account for this mismatch and be able to update our control actions. So traditionally, with this quadratic stage cost, the notion of stability is that you drive the state toward the steady state. So this formulation of MPC on its own does not guarantee that you do that. And so there have been a lot of ways that people have looked at modifying this control law in order to be able to make theoretical mathematical guarantees about being able to actually approach the steady state. And so that's what model predictive control is. How do people typically use it in next generation manufacturing and the process industries? Well, the typical way has been actually in a hierarchical approach. So you can see here this hierarchical approach. There's a steady state economic optimization problem that's solved to determine the economically optimal steady state to operate at. That's sent to the tracking model predictive controller with that quadratic objective function. And then that quadratic objective function is then centered around this economically optimal steady state. So the MPC is going to compute control actions which drive us toward the economically optimal steady state, and that will help us run our process. Now, one of the disadvantages of this that has been looked at for quite a number of years now is the idea that this separates economic optimization and control. So maybe instead we could combine them. And when people combine them, it's what we call economic model predictive control, or EMPC. And so the idea of this is that we say, we do not have to use this quadratic objective function. We can use any objective function we want, and it could be representative of our process economics. Now our controller is explicitly optimizing economics constantly instead of just trying to drive us to the steady state. And then we would need to try to figure out, how does that controller work? Does that still guarantee stability? And there's been a lot of work on that over the last approximately 10 years or so, as people have been trying to better understand what are the implications of changing that objective function on the stability that we get for this type of control law. And so the basic components of this type of controller look very similar to what we had earlier with the standard model predictive control. The main difference is that you change this economic objective function. And so, of course, you can also add additional constraints if you would like these input rate of change constraints, which say, well, maybe the control actions I'm computing when I'm trying to optimize economics might be more aggressive than I would have gotten if I was just trying to drive to a steady state. I'm going to put a rate of change constraint to try to prevent aggressiveness of my actuator use. But as mentioned, one of the big questions is, how are we going to update this control law in order to maintain stability or safety? So one of the approaches that inspires a lot of the work that I'll be talking about today is what's known as Lyapunov-based Economic Model Predictive Controller, LEMPC. And so this has the same format as the LEMPC, or sorry, as the EMPC on the prior slide. There's a slight change to the way the input rate of change constraints are denoted here for feasibility reasons. But the big change is this new Lyapunov-based stability constraint. So what this one does is it says that the value of the Lyapunov function has to be less than or equal to this upper bound rho e, which means that the state has to be maintained in the subset of the stability region. And then there's a second mode of operation of this controller that says, instead of keeping the closed loop state in omega rho e, drive it toward the steady state. And so the combination of these two modes of LEMPC can guarantee that with sufficiently small plant model mismatch, we're always able to keep our state in the larger stability region, omega rho. So that's a notion of being able to guarantee safety under this control law. And so now that we have some background on the type of advanced control laws that I'll be talking about, we can start moving into the cybersecurity question. So one of the first questions is, do cyber attackers really care about attacking controller manufacturing systems? And the answer that we can see in quite a number of case studies is yes. And so just to go through a few really quickly, one of these is Stuxnet, which happened in 2010, and it was an attack on Iranian nuclear facilities that was able, through a worm that entered the systems via USB sticks and spread, to run centrifuges at conditions that ran them out of their operating range and was breaking them. There have been a lot of other things since then. For example, part of the Ukraine power grid being taken down in December 2015, malware that could prevent safety instrumented systems from activating when needed. There was the case of a remote user changing sodium hydroxide levels at a Florida water treatment plant. And then there was also the case where a company was worried about whether or not their operational technology had been compromised when they got a ransom note requesting payment on a company computer, and so they shut down the Colonial Pipeline. So the outcome of all of these is yes, cybersecurity of process control systems is an important issue. And one of the particular problems with cyber attacks on control systems is that control systems really rely on the notion that our measurements of our state become related to the control actions that we take. But what cyber attacks do is they remove this association between the state measurements and the inputs we apply. And so one thing that we can do is we can say, let's try to understand mathematically what that means. So for example, we can say, let's say there is a specific type of attack, a case where the sensor measurements never make it to the controller. Instead, we're sending false state measurements to our controller. In this case, what would it mean for us to be cyber attack resilient to this type of attack? Well, mathematically, we could put some conditions like there would have to be no possible input policies I could ever calculate given the controllers I use and their implementation strategies, such that my state leaves a set of safe states for any allowable initial condition and any disturbance trajectory for all time. Now, the problem with this is that is not very constructive. That does not really help us figure out any type of resilient control design. And so let's take a look at a process example to help us gain a little more insight into what it means to be cyber attack resilient versus not. And so this specific process example is motivated by the idea that an attack might be designed to try to reverse engineer a known control law. So specifically what I mean by that is that, say someone wants to attack your sensors, if they know the relationship between your sensor measurement and your input that you're going to apply, if they give you that sensor measurement, then what they want to do is figure out what's a bad input for your current process state, and then back calculate what sensor measurement they need to give you in order to get you to calculate that input, and then tell you about that. So one idea that we might have in that case is to say, well, maybe I could try to randomly select the controller I'm going to use at a given sampling time. Maybe that will make it more difficult for the attacker to reverse engineer my control law and figure out what problematic state they want to give me as a false state measurement. Now, using randomness in any control design would only be allowable if we would actually maintain closed-loop stability or safety during our normal operation. And so we did develop an implementation strategy that involves a set of LEMPCs and of other stabilizing control laws. And at every sampling time, we randomly select one of these until we find one for which the state measurement that we have is within the stability region of that control law. And then we are able to apply that one to the process. So let's take a look at how well that works. So here we'll have, again, a continuous stirred tank reactor with a second order exothermic irreversible reaction. And our control objective is to regulate the process in an economically optimal, time-varying fashion while maintaining closed-loop stability. And so we have here some manipulated input constraints. We're going to have our objective function being related to the production rate of our product. And we'll also design Lyapunov-based stability constraints for this system. And then we will design 6 different LEMPCs for our system and also an explicit stabilizing controller. And we'll randomly select between our different 7 control laws. So here on the right, what you see is you see a lot of different stability regions for a lot of different controllers. And then you see the closed-loop state looking like it's going crazy with time as we operate it in the absence of an attack under randomized control law selection. But what we see, even though it looks a little crazy, is that the state actually did stay within the largest stability region. So we could say that was actually what the goal was. So it seems like it was doing fine in the absence of an attack. So what happens if we add the attack? So in this case, we're going to have a false sensor measurement. We apply it to a single LEMPC and then also to the case that we're using our randomized LEMPC implementation strategy. Now, the results do depend on the seed to the random number generator, but in all the cases that we tested, there was not a very significant delay in the time that it took for the cyber attack to cause operational issues for the single LEMPC versus the randomized LEMPC. And the way that we characterized these operational issues was by setting this threshold on the temperature and saying we never expect the temperature to go above those values when we're under normal operation, and let's set that as our threshold. So you can see here in a very short time after operations started, in fractions of an hour, we were already getting the temperature above these thresholds, regardless of whether we were using the randomized strategy or we weren't. So the problem here is that the randomized LEMPC implementation strategy really could not guarantee that you would never be able to calculate a problematic input over time. So this really demonstrates that developing a control theoretic understanding of how to get cyber attack resilient control designs is very beneficial and is needed in order to be able to be successful at fighting off the attackers. So this led us to consider maybe detecting attacks and how detection algorithms could work together with control laws to try to be able to flag the attacks before they cause a problem. So we tried a number of different strategies to try to understand when these different ideas would or would not work for that. So some of the things that we looked at was, for example, an LEMPC strategy that tries to probe for cyber attacks actively. So it tries to say, maybe there is one, let me check if I can find it. Then there was another case where we were using a more passive detection strategy, and this one was based on getting state predictions and comparing them with the measurements we were getting. And then there was another one that uses what's called state estimators, and it was comparing the estimates against each other. And so I'm going to go into a little more depth on that one now. So the idea here is that we have M sets of measurements and that these are continuously available and that we have these observers or state estimators that have a special property that there is a time after which the state estimate becomes very close to the actual state. So there's a bounded error between those. And so now let's consider what happens if we design an LEMPC, but now the LEMPC is getting a state estimate instead of getting the full state measurement. And so in this case, if our estimate was to be wrong, because maybe our state measurements were wrong that were used by the estimator, then this could be a problem for our control law. We might get a destabilizing effect. But we said that we have a number of different estimators, and so that gives us a level of redundancy. They could cross-check each other. So because we know that there is a time after which if an estimator is correct, it becomes within a bounded amount of error of the actual state, then this implies that when there's no attack, any two estimators should be within a bound of each other after some amount of time. So this means that if we notice that they are not, we should flag it as an attack. And we have also been able to prove that if these two estimates are within a bound of one another, as long as at least one estimate is not impacted by an attacker, we can actually maintain safety of the state at all times before the attack is detected. So one thing that comes up with regard to these ideas of how to handle the cyber attacks on sensors is the question of how is that different, or how are cyber attacks in general different from handling, for example, faults on the equipment? So this really starts to come through when we start looking at handling simultaneous actuator and sensor attacks. So to do this, let's go back to our continuous stirred tank reactor. So again, we're going to maximize our economics related to our production rate of our product. But in this case, we're going to have a manipulated input constraint where we're only going to have one input now. So this is only going to be the concentration of reactant in our feed. We're going to design a new Lyapunov-based controller for this system. And what we're going to do is give full state feedback to our LAMPC. So in terms of the attack detection policy that we're going to use to showcase how attacks are different from faults, we're going to use the following one. We're going to check if our Lyapunov function is decreasing over time. And so we do expect that it should be, because, for example, let's look at the case there's no attack. This here represents the actual value of the Lyapunov function. And these represent the value of the Lyapunov function that we get from the sensor measurements, which could be falsified. So these are not necessarily always correct, but this one is correct. So here in the case that we have no attack, we see that the value of the Lyapunov function is decreasing for both the actual Lyapunov function and then also for the one that we evaluate from the sensors, which is actually underneath this blue plot. And so this is a fine way of detecting the attack over this sampling period. So then let's see, when are attacks discoverable? So we could do an attack on the actuators. And so in this case, we get the actual value of the Lyapunov function is increasing. It's under this blue line. But then at the same time, so is the evaluated one. So that's shown in this black line over here. And so we would detect that attack and say, oh, the Lyapunov function is not decreasing. And we could look at other cases too, where we say we have a false sensor measurement or combined actuator and sensor attack. But the most interesting is when we look at a stealthy actuator and sensor attack. So in this case, what happens is we have this blue trajectory here on the left and on the right. So what we see is that the actual value of the Lyapunov function is increasing under our stealthy attack, whereas the one that's apparent from the sensors is decreasing. And so the reason for that is that what the stealthy attack is doing is it is doing an attack on the actuators while at the same time making the sensors mask that attack and show data that makes it look like everything is fine. And so this is really where the fundamental difference between faults and attacks occurs, is that usually faults are not everything failing at once in ways that are trying to mask you from noticing that there is a problem. Whereas cyber attacks, that would be one of their characteristics. And so because we can see that there can be these challenges with these simultaneous attacks, one of the things that can make us think about is how can we extend the methods that we developed previously for trying to detect attacks on our sensors to the case that we have attacks on actuators or both actuators and sensors at once. So we have actually done some of these extensions and been able to put together multiple types of detection strategies in order to be able to detect the attacks before they cause problems. And so now I'm going to pivot a little bit to the quantum computing aspects of this talk. And so as mentioned earlier, this is not explicitly related to cybersecurity, but it is related to cyber-physical systems. And I think in the future, you never know where this will go. So this is really at an exploratory phase for us right now. So what we want to look at is what would it look like if you implemented control algorithms on quantum computers? So as was mentioned earlier, today we implement control algorithms on classical computers because control algorithms are, or controllers are really just computers. So what would happen if they were quantum computers instead? So for this, we need a little bit of background on quantum computing. So information on quantum computers is stored in qubits. Qubits are the quantum computing equivalent of bits in classical digital computing. And one of the interesting things about quantum computing today is how much you need to understand quantum physics in order to be able to follow a lot of the things that happen in the literature. But one of the things that's interesting is the notation that gets used for representing the 0 and the 1 states. So this weird symbol is called a ket. And so this is ket 0 and ket 1. And in quantum computing, the mathematics is really governed by matrices and vectors. And so here we can see the vector notation of ket 0 and the vector notation of ket 1. And you can get superposition states on a quantum computer where you can have a superposition of the ket 0 and ket 1 states. And so you can build quantum circuits through a series of logic gates that act on the qubit state. And when you're doing quantum computing, the gates are represented through matrices. So for example, this gate up here, H, in this circuit, is represented by this matrix when you're looking at what action it has on a qubit. And so we can put together a lot of gates, and these can form important algorithms. So here, what we have is an addition algorithm. And so this will take the binary forms of two integers, A and B, which are put here on the qubits in binary, and then it will run them through the series of gates. And by the end, what you get back is you have some qubits that are in the states that correspond to the bits of the sum of A and B. And so there are actually ways to get code for this that we drew on heavily. And so this came from GitHub. And so what we're going to do is we're going to use this quantum Fourier transform based addition algorithm in order to start to look at the intersection between quantum computing and process control. And so the idea here is that we'll have this relatively simple dynamic model. It says that x dot equals x plus u, and the control input that we're going to use is negative 2x. So this is a stabilizing input when we use a classical controller, if we have continuous sampling. And the quantum Fourier transform-based addition algorithm can be used in this case because 2x can be computed as x plus x. So if we get a measurement of our state, then we can send it to our quantum computer and say, please add the state to itself. And then we can negate the answer after and use that as our control input. So quantum Fourier transform-based addition is actually a deterministic algorithm in theory. And so that means it should give us exactly the same results as the classical computer in theory. So what's interesting about this case then? Well, today's quantum computers are actually not perfect. They have noise, and so they're not yet fault tolerant. And so this can cause the result of a series of gates to be non-deterministic in practice, even if it should be deterministic in theory. So that's where the interesting thing here lies. What will happen if we start using control actions that are being computed on a computer that's having faults, so that it's actually not always computing the control action that you expect? And so one thing that we have to do is figure out how we're going to get a simulation going for this case. So IBM actually does have something called the quantum experience that anyone can go on, and they can actually use real quantum computers on there. But the problem is the ones that are available for free are pretty small. They only have a few qubits. And at the time that we did this, there was only 1 qubit and 5 qubits available. So that's like having 1 bit or 5 bits for doing computations. And that's really just not a lot to do much that's meaningful. And so what we wanted to do was use what's called a quantum simulator that's also available from the IBM Quantum Experience. So this tries to replicate some aspects of the mathematics and physics of a quantum computer through a program that's being executed on a classical computer. And one of the things that it has is it has this ability to incorporate what's called a noise model. And so there are different ways to get that noise model. But one of the ways that we wanted to do this was we wanted to use the 5-qubit quantum computer, and we wanted to try to see whether or not the noise model that we were using seemed consistent with a noise model that could come from a get noise from backend command with respect to this 5-qubit quantum computer. So then what we need to do was choose a circuit that we were going to use to help us make this evaluation. And so we chose this circuit here that represents a controlled rotation gate. And so here we see the results. Here on the right is the results from using the get noise from backend command related to the 5-qubit quantum computer. And here is the results from using a depolarizing error noise model. And we see that they were approximately the same. And so we use this then as a benchmark to say, okay, we think this is a sufficient noise model for us to start to analyze the control actions that would be determined by this noisy quantum computer. And so now what's left is to look at the state and the input trajectories being computed. And we're going to look at that in multiple cases. So we're going to say, what happens if we use our controller on a classical computer? What happens if we implement it on a quantum simulator with 254 shots and no noise? And we'll call this the ideal quantum system. And if we use a quantum simulator with 254 shots and noise, which we'll call a noisy quantum system. Shots here means the number of times that you run the quantum algorithm. So what we were doing is we would run it a certain number of times, and then we would run a Python command that would take one of the answers that had been computed the maximum, or the maximum number of times. So if there was not one that was only the max, then it would return one of the answers that had been there the maximum number of times if there were multiple. And so we start our state at this initial condition of 7.4. And then we see when we use the classical system and the ideal quantum system, meaning no noise, as was stated before, quantum Fourier transform-based addition is deterministic, so we get the same results. But when we add the noise in the quantum system, then we start to get this green trajectory, which deviates from the others. And so we can look at other permutations of this. For example, we can say, well, what if I only use one shot? Well, then it looks a bit worse. We can change our initial condition to start closer to the origin. And then we can see that here with one shot, it doesn't look quite as bad. There are some interactions between how many qubits it takes to represent the number that you're using as your initial condition, and then how many possible answers there could be when you have the noise. And then if we use a lot of shots when we're pretty close to the origin, we actually were able, in some cases, to get all three sets of results to match each other. So these are some preliminary studies related to implementing control on quantum computers, and they indicate that there might be some promise for the future of being able to do this, but that this had nothing to do with whether or not it was a good idea or computationally feasible or any of that. This just was looking at purely what happens if you have noise from these devices. So in conclusion, next generation manufacturing values flexibility and profitability. This is facilitated by automation advances such as economic model predictive control. And a challenge, though, is that flexible and profitable systems may not be secure. So attacks on control systems could undermine process safety. We've looked at things like integrated decision and control policies that are geared toward nonlinear systems. And these have the potential to enable attacks of various types to be detected before they cause safety issues. But the work that we've been doing is very control theoretic. So this does mean that in order to actually get the resilience guarantees that we're looking at, we would need to find ways to meet all of the theories in a practical system. There also can be some requirements, like that some aspects of the system probably still need to be secure, like maybe some sensors or some actuators cannot be hijacked. And we also looked at quantum computing, which is another interesting potential direction for the future of next generation manufacturing, but really requires a lot more research in terms of both the control theory and also algorithms before being able to determine whether or not this is worthwhile for any future endeavors. So I will like to thank our funding sources and then also my great PhD students who have done the work that was shown here today. And so thank you so much for your time, and I will be happy to take any questions.
Okay, thank you for a very nice talk, Helen, and bringing chemical engineering perspective on cybersecurity. I really appreciate that. Are there questions from the audience? And I'm going to shut off my mic as often as I can because I have some background noise. But anyone else, unmute yourself and go ahead and ask some questions. Gabriel has put the survey in the chat, so everyone please take the survey. So yeah, what you've said there's some ways this can be used, and say somebody was, let's say the reverse happened, that an enemy was trying to hack one of our centrifuges or whatever. Have you done some of these some of these detections in real life, and can you give some examples of that?
Um, yeah, so in terms of like simulation study, so a lot of our work has been focusing more on trying to understand like what it would take to develop something that's cyber attack resilient. More than demonstration. Our work is purely computational, but some of the systems that we have that are larger scale that we have looked at is we had like a computational fluid dynamics and finite element analysis model of a portion of a steam methane reformer, where one of the students was looking at what would happen if someone was to like manipulate very quickly some like boundary temperature, and then how would that affect the stress in the wall differently from how it would affect the like hydrogen profile, for example. And then of course we do some simulations on a smaller scale with these continuous stirred tank reactors, but those are more for helping us to understand like um, where the challenges and limitations of the methods that we're proposing, so that we continue to keep trying to advance and understanding where we need to improve the algorithms that we're developing.
Good. So when you say you do a simulation on a CSTR, that simulation is virtual only, or have you actually
Yeah.
done like gone to Unit Ops Lab and done any can you and when if you haven't done that yet, are you planning to? And how would that what would you be looking for?
Yeah, I at this time we're not really planning to do experimental work with this. The reason is that what we're really trying to achieve is trying to understand like what should be the sort of the cyber infrastructure of the future for the most like agile next generation manufacturing strategies that we can possibly get. And we tend to think that that like that really takes a lot of trying to do the fundamentals and say like, okay, would this be secure, when would this be secure, and like what would it take to get like the minimal cost security, and really trying to understand that. So I think right now we're more proposing different methods and trying to, through the theory, understand the fundamental limitations of what these algorithms can do, so that then that we can in the end sort of maybe stack them up and sort of do a cost analysis and say like, should anyone switch to these, or should industry just keep using the standard like IT things? We really want to understand, I think, that question more than just trying to see what it would look like to do the cyber attack. So I think we just have a different focus.
Okay, thank you. Other questions? I'm looking at our audience here. Brendan, do you have any questions? You're the person that wants to do some of this, and he's wanting to apply it in kind of real life. We're actually going to buy some sensors and kind of try to get started at a very
Wow,
low level. So
that's really cool.
Yeah, I think you answered the question, same question that I had from Bernie. But thank you for the seminar. It was really interesting.
Thank you. What are you gonna look at like in your, I don't know if you if you prefer to talk about this after. I'm just curious, like what is your research goal? Since I said sort of like what ours is, but like what are you gonna search for when you do the real experiments, since that's something that I'm not planning to do. So I'm really curious, like, ooh, what kind of things are you gonna probe for? That sounds interesting.
Yeah, so we're kind of interested in seeing what happens if our reactor process gets interrupted. So what we want to do is develop a software that monitors all the important parameters in our process. And so see if someone is able to hack into that software and adjust like what the actual oxygen reading or the amount of glucose in the system, which is really important. We want it to be able to restore to a specific range so that it doesn't harm the cells. And just looking at long term how those kinds of small changes can affect how our cells behave. Yeah.
Okay. Yeah, I can imagine that, like, especially with something like cells, where I think there's still, like, I don't think they behave quite as deterministically as like we imagine chemical process. I don't know. I don't know a lot about
Oh
cells,
yeah,
but that's
that's right. They're very complex.
yeah, that sounds like a really interesting problem then, like experimentally to sort of like you're saying, say like what would even happen if someone attacked these? Like what could they even really achieve? That's really cool.
There have been some biotech examples where someone was manufacturing a protein, and it basically has a series of amino acids that need to be linked together for that protein to be made. And someone had hacked in
Oh my
and
goodness.
put in a different sequence,
Wow.
and so they actually made a toxic protein rather than the real kind of therapeutic protein, and they were able to catch it um, before
Wow.
went into mass scale or actually mass distribution.
Oh my
So I don't
goodness.
know a whole lot about it, but maybe you've heard of some of those kinds of things. But yeah, there's in every area there's potential for hacking and disturbing processes.
Wow. I had not heard of that one before.
Yeah.
That's scary.
It is, isn't it? Yeah. Okay. Other questions? Okay, well, today is actually a university class holiday because of President's
Mm,
Day. But we decided that we would invite our students anyway, because this is not really a class that they're getting credit for.
yeah.
And then we invited our normal, people that come to our normal seminars, and a few of them have come um, on their own. It's kind of voluntary basis. So we really appreciate you taking the time to spend some time with us, and um, would love to be in touch in the future. Like how do we take this? I mean, it's for us, it's rocket science. I know it's not for you, but how do we apply this Lyapunov type of system to Brendan's project, for example?
Yeah. Yeah, thank you all so much for coming even on your holiday. Oh my goodness, that's so kind of you.
Shola, did you have a question? You showed up on the screen.
I think you're
Or we
muted.
can't. Yeah, you're muted.
Can you hear me?
Yeah, now I can.
All right. I don't, but I just want to say a big thank you um, for the excellent presentation. Really, really well done. Thank you so very much. And thanks to all the students and partners who showed up. I mean, we had such a good crowd, about 30 people here, even
Yeah.
on a public holiday. Well, there's, as Bernie said, we do not have any classes at WSC today. So thank you to everyone.
Yeah,
Yeah,
thank you so
yeah.
much.
Yeah, I want to thank everyone for coming, and please go ahead and fill out the survey. Shola is the external evaluator for our project, and he's the associate dean for educational, or not just Ed Psych, but the College of Education. And so he's put together the survey and helping us with those kinds of things. His undergraduate degree is in computer science, and so
Wow.
he's very interested in this kind of thing. Okay, well, Helen, we'll let you go. Thank you so much for taking some time to meet with us. I know it's evening for you, and so
Well, thank you so much.
yeah.